So B induced is going to point like this. Now you may wonder why I don't have it perfectly against the external. Well, that's just because you can't have current flowing any way you want. It has to flow within the ring. So you only have two choices. So it can either go around like this and make B induced like that, or around like this and make it like that. So it's constrained to actually moving along the path that you have. The charge just can't jump out into space and make a perfect B induced against it. So if our choices, out of our two choices, the induced current is going to flow like this, and we're going to have that B external and B induced are as opposite as possible. And that again is true because the flux is increasing. So let's go ahead to the next one. So this is barely, this is not even a quarter of a rotation later. This is just a little bit later, right? We've just basically come up to the top, just gone a little bit past it. Flux is decreasing now. So we're basically looking just before and just after the maximum flux, right? So we're either climbing up to the maximum flux, we're increasing the flux, or we've just passed it and it's decreasing again. So now, does the B induced want to point more with or against the external field? With, okay? So we have two choices. It can flow like this and make this magnetic field, or it can flow like this and make this one. We choose this one because, of course, that's as with the external as we can get. And using the right-hand rule, the current is now like this. So to recap, now B external and B induced are in the same direction as much as possible. Okay. So what do you notice about the direction of the induced current comparing these two? It's opposite. The current reversed directions. It's no wonder if the flux keeps on increasing, decreasing, increasing, decreasing, increasing, decreasing, then the current trying to keep up with that opposition is going to have to slosh back and forth to try to keep up with these changes. Okay? So I induced actually reverses direction. This is the first time we've seen this where a current will literally slosh back and forth all the time. This is what we call AC. AC stands for alternating current. This is to distinguish from everything else we've seen in the class before, which is called DC, or direct current, which means that the current always flows in a given direction. It doesn't necessarily mean it couldn't change the amount of current. For instance, in RC circuits, we saw that the current amount changed over time, but it did always flow in the same direction. So that was DC. So any circuits that have the resistors or capacitors and batteries, those are DC circuits. But this is the first time where we've conjured up a situation where the current will actually slosh this way, then this way, then this way, then this way, okay? So let's work out the details. Same law. Have it here already for convenience. So let's do it. So flux, again, the ingredients, N, B, A, cosine of theta. And remember how that theta is measured. It's between the normal line and the external field. Normal line and the external. In this system, that angle grows from 0 to 90, which is the maximum, and then back again. Back and forth, back and forth, back and forth between those angles. So let's go ahead and work it out. N is constant, B external is constant, A is constant. The only thing that changes is theta. Now, I guess I should mention, if you've been wondering about the absolute value signs, the absolute value signs are there because for the most part we want to keep EMF positive. We don't really think of EMF as having a sign, so we just basically are trying to make EMF come out positive. This is one of the cases where no matter how hard we try, we can't stop there from being a sign that pops out, and so I'll say a few brief words about what that would mean. So first of all, one of the things that's kind of annoying here is that the theta, which is changing, is actually trapped inside a cosine function. That's the only, out of the four variables, n, b, a, and theta, it's the only one that isn't kind of out already. It's kind of trapped inside a function. So we need to figure out what to do here. So that theta, by the way, you can mark that theta. That theta is this here. It's this here, right? It's the angle between, whoops. It's the angle between the normal line and the external field. That angle, I'm going to characterize in a different way. I'm going to say that theta is omega times t. Now, this may ring a bell from Physics 1, maybe not. It's one of the constant angular acceleration equations, but there is going to be no acceleration. So this is basically just distance equals rate times time. It's just in the angular world. So this gives us the angle in radians. And omega is your angular speed, radians per second. And you multiply it by seconds. So I'm basically choosing, instead of talking about theta, I'm talking about the angular rotation rate, omega, times the time. So it's not really so different from delta x equals v times t, right? So it's just the angular version. So what I'm going to say is that I am applying a constant omega. So by some external means, I am applying a constant rotation rate to the ring. And then if I want to know what angle it is at any given time, I just multiply that by the time. By the way, this formula also seems to suggest that t equals 0. I have to start off at 0 degrees, but that's fine. Who cares where it starts? It's the change over time that's really where all the action is, right? The change of time is what leads us to anything useful. So what I'm going to do is I'm going to substitute the theta that I will be at any given time will be my angular rotation rate times the time. So now we have to figure out what's going on here. This thing, including absolute value signs, becomes this. Now how did I get that? Well, that is a simple derivative. If you have taken calculus, the deltas are just thinly veiled derivatives. And if you've never seen calculus, it's magic. I got that with magic, okay? So this is one step where there is no way to get around a little bit of calculus, and of course I don't expect you to know how to do this derivative, so you will find the result on the equation sheet. Let me fill in the rest of it, of course. And let me not bother to draw b external because that's annoying me. So that is my final answer for the EMF produced. Okay. So this equation can be found on your equation sheet. And I want to take a little bit of a time to explore it, and if only to tell you that we're not going to be terribly concerned with going crazy on this equation. The main thing of interest I have in this equation is this thing here. This thing here is basically the multiplier on your sine function. So let me sketch this. The EMF versus time. Well, it looks like a sine function. Hopefully that's a familiar looking thing. A sine function normally in math class, if it doesn't have any multiplier in the front, what is the maximum value that the sine function bounces back and forth between?
1.
1 and -1. Well, we don't want our EMF to bounce back and forth between +1 and -1 volts, because why is it always 1 volt? That's weird. So this here is basically sets the maximum fluctuation of the EMF. So it goes plus Emax on here and minus on the other side. So this is definitely the first time where, despite our best efforts, we do have a sign on the EMF. So I'm going to say a few brief words about that. It's no big deal. Here's what we have. When we have a DC circuit, we have a source of EMF like this. We draw it like so. There is absolutely no reason to call it negative. And the current that it causes, which is in a well-defined direction, is also, there is no reason for it to be negative. The one exception, I guess I should mention, is when we did Kirchhoff's laws, right? We occasionally solved and got a current that was negative, and then we just said, oops, that means it's flowing, we guessed the wrong way. Well, now, we're going to look at AC circuits where currents flowing back and forth is what happens. So first of all, how do we draw an AC voltage source, like the one we have now? We draw it like this. It's just a little circle with a little squiggle in it, which is basically a little piece of sine function. The reason why we draw it like that is because there is no defined place that is always at higher voltage and always at lower voltage. When we draw a DC source, it's understood that the terminal, which is a higher voltage, where the current comes from, is drawn longer, and the one that it goes into is drawn shorter. So what we will find for an AC source is that when the EMF is positive, that means it sends current one way, like this. It's effectively functioning like a battery where the higher voltage terminal is on the top. But then, later, we draw the EMF being negative means that the current is being sent in the other direction. So if we set one direction to be the positive current, when it switches direction, that's negative current. It's kind of like a number line, right? Once you pick one direction to be positive, the other direction is negative. So at this time, it functions like a battery, but with the higher voltage terminal on the bottom. It basically flip-flops back and forth its terminals. Okay? That's what AC is. It sends current one way, which we call positive, and then later it switches it the other way. We call that negative, and then back and forth and back and forth. So that's what we see. From here to here, the current is positive, or the EMF is positive, and so the current will be positive as well. In fact, by the way, the current function, that's going to be easy enough. Just use Ohm's law, divide the voltage, right? The voltage is what's driving the current. So we're going to get this. So there's my current function. And notice that the multiplier here, which is of course I max, is just the maximum EMF divided by the resistance. So basically, the current function looks identical to the, I guess I can sketch it out here real quick. The current function basically looks exactly the same. Okay? When the EMF is positive, the current is positive. When the EMF goes negative, the current goes negative. Okay? So what do I want you to know about this? Well, I want you to understand that what the sine function accomplishes is the sloshing back and forth. I'm not going to ask you to do anything with it other than that. I just want you to understand the concept of it. I'm much more concerned with you understanding what factors go into how big this oscillation is. Okay? So let me write that down over here. That's the interesting part to me. So I want you to understand why the current sloshes back and forth. That's what Lenz's law dictates. We get true AC. And I want you to then just understand, and I guess the other point I should make is that, is this going to change much because the current's sloshing back and forth? Well, imagine sending AC through a light bulb, okay? So we learned, of course, what's a light bulb? Light bulb is something where you send current through it, the electrical energy gets dissipated into thermal energy, and the thing gets so hot it glows. So what if we then took a light bulb and we sent current that went back and forth? Does it still get hot? Yeah. It's like saying you can only heat up your hand by going in one direction. Of course, it's not true. So if you send current in that's sloshing back and forth, yes, it's more complicated to analyze because it's not a constant voltage, but the effect is still the same, right? You're still going to turn energy into heat through a resistor. So the sloshing back and forth is not that consequential. Question?
What about the resistance decay over time? Like, depending on the material, won't that like decay and at one point it'll just show?
The resistance
of the resistor, like,
yeah,
won't it just break at a certain point? It like a light bulb over time will just break.
Yeah, I mean, it's basically when you're dissipating that electrical energy into thermal energy.
Yeah.
You raise the temperature, but hopefully under the melting point, right? If you raise the temperature too much, it'll melt immediately. You don't even have to wait. I used to have a demo where I ran a car battery charger through a paperclip, and the paperclip would basically explode. It would also just ruin the charger, so I don't do it anymore. But yeah, I mean, the whole idea here is that, you know, eventually you can have the resistor burn out. You know, in a electrical device can work for years if you treat it right, though. If it's able to take that thermal energy and vent it to the environment before it gets too hot. So let's look at what goes into the maximum EMF we can get. Okay, the peak EMF, which will, of course, when you have peak EMF, you'll be driving peak current. So first of all, what do we want to do? We want to have as many loops as possible in as strong a magnetic field as possible. We want to have as big of an area as possible, and then we want to, of course, rotate it as fast as possible. These will all increase the maximum EMF and the maximum current. And while we're at it, of course, we could say P equals I squared R. So at maximum current, it'll increase. The larger the maximum current is, the larger the maximum power dissipation. Okay? So those are all the things we want to do to make the power dissipation in the ring as much as possible. And I guess I should point out that if it doesn't matter how big these three things are, if the rotation rate is nothing, then you get nothing, right? Can anyone tell me why you get nothing if you don't rotate it? So if you don't rotate it, there's no flux change, right? You can have a lot of flux, but it's constant in time. So rotation is absolutely necessary. Remember, something has to change with time. In this case, the angle changing with time, and that's reflected in the rotation rate, omega, right? Okay, so let's take a look. I have this very thing here with me. So you can't see it, but inside there is a large stack of wire loops, a big coil. And I guess I can draw it. I have something like this. and they're on an axle, and they're attached to a hand crank. And it's not just one, but probably thousands of loops, because that's going to get me a much larger influence, right? Then around it, I have horseshoe magnets. Horseshoe magnets are bent so that the north and south pole are opposite from each other. Remember that magnetic field lines point from north to south outside the material, so they're basically like this. Now, one magnet isn't that strong, so there's actually 3 of them, all with their norths lined up to make a super north, to make it a stronger magnetic field. So I have a large amount of turns in a large magnetic field. The area of them isn't that big, but if the area was bigger, I couldn't, it wouldn't be transportable in here if it was the size of the room. Okay? And then the final factor, which I need to supply, of course, is the rotation rate. And there will be current induced, AC current induced in the coil, and that is harnessed out coming out through this light bulb. So we're going to get a chance to see what happens. So I can rotate it slowly. Okay, get a little bit of power dissipation, right? And then if I rotate it faster, it'll glow more, okay? Does that make sense? Now you may be wondering, like, if the EMF is sloshing back and forth all the time, why don't we see it flickering? Of course, here there will be times when the EMF is 0 and there's no current. Well, let me tell you this, thermal energy doesn't go right away. So if you make something hot, right, it's not immediately going to cool down, right? It's like if you put a pan on the stove for a while, then you just turn off the stove, don't touch the pan, okay? Yes? You know this, okay? So even though the power dissipation is now sloshy and it's not constant, the heat that goes up and makes the filament hot, it will stay hot with this kind of continuous injection of power, okay? So this thing, what we've just talked about, is called an electric generator. Electric generator. Now this might seem like a little bit of a parlor trick. I have to go up and turn the crank, okay? But this is how all power is generated. The only thing that you're doing in different forms of electricity generation is finding different things to turn the crank, okay? So if you work at a power plant, you don't literally clock in and grab a turn and turn the crank. That would be silly. There is something else that you're going to use from nature that is turning the crank. So to give you some examples, let's have a hydroelectric plant. So you dam up a bunch of water, and if you don't want to generate an electricity at that moment, it's just a dam. But when you want to generate some electricity, you will notice water shooting out the bottom of the dam. What's the water for? It's to turn the crank, okay? So you use the water to turn the crank. It rotates some conducting loops against some magnets. Out comes induced current, AC. It gets sent to your house, okay? So you can say take some coal or natural gas or something like that, burn it, get some water to be some steam, have steam turn the crank, okay? And then I'll put a bunch of other weird greenhouse gases, right? Okay? So that's another way to turn the crank. You can use nuclear fuel to heat up some water into steam and turn the crank. No greenhouses at all there, okay? Whatever weird way you want to turn the crank, you're just turning the crank. You're turning some magnets against some wires, and you're making AC, and that's where we get electricity, okay? There are different ways to turn the crank. So for wind power, you literally use the wind to turn the crank. So you see those big wind things? They all have inside them magnets and wires. That's what you're really turning when you turn the windmill, okay? The only form of energy that does not rely on this principle that I can think of is solar. Solar is a little different. We'll talk about a little bit about how solar works. Solar actually produces DC, okay? But all of this output from all of this stuff, hydroelectric, fossil fuels, nuclear, it's all producing AC electricity through this mechanism. It might not be exactly this in the details, but it's basically turning some wires relative to some magnets. Okay? Are there any questions on that? Okay, you can feel free to come up and try to turn the crank if you want, and see how much you can get here. Just to give you an idea of energy, right? This right here is a decent amount of effort to get that much electricity. So just to give you a little bit of a concrete sense of how incredibly energy hungry our modern society is, right? The amount of energy that goes into electricity is pretty extreme, okay? Even when they were first introducing electricity, they had no idea